In this video, we're going to do some exponential derivatives examples. So we're going to remember three laws that are pretty key. The derivative of ln x with respect to x is 1 over x. The derivative of e to the x with respect to x is e to the x, and the derivative of b to the x with respect to x is b to the x ln b. And then putting that together with the chain rule, the derivative of b to the f of x will be b to the f of x times ln b times f prime x. And that's assuming each of those last two rules that b is a scalar. So a short way of saying this is to differentiate an exponential function, determine the derivative by simply restating the function and multiplying by the natural logarithm of the base and also by the derivative of the exponent. Now, this is assuming that x is in the exponent but not the base. There is a different rule if x is in both the exponent and the base, and that will be in a later example, later video. So suppose we had the function g of x equals e to the x squared minus x, and we want to determine the derivative of that. So we could simply say g prime x is equal to, we're just going to restate the function, and then we're going to multiply by the natural logarithm of the base, and we're going to multiply by the derivative of the exponent. The exponent's x squared minus x, so the derivative will be 2x minus 1. Now, since the base is e, the ln of the base will be 1. So whenever the base is e, we actually don't have to show that part. So we can simply say the answer will be 2x minus 1 times e to the exponent x squared minus x. And that's shown on the next slide. Okay, so it's there on your screen, written out a little bit more neatly. So what if we have the curve f of x equals x squared e to the x? Well, I see there an opportunity to use the product rule. So f prime x is just going to be the derivative of x squared times e to the x plus x squared times the derivative of e to the x, which of course is just e to the x. And I get that expression that you see on your screen. And so this is us showing it typed out, and then we can factor out e to the x, and we'll be left with a second factor of x squared plus 2x. Okay. What if we want to determine the equation of a tangent line to a curve y equals e to the x over x squared, specifically where x is equal to 1? Well, what we're going to need there is the slope of the line and a point on the line. So we're going to determine the derivative of this function by using the quotient rule. We have the denominator times derivative of the numerator minus the numerator times derivative of the denominator all over the denominator squared. At x equals 1, we'll be able to plug a 1 in. We get 1 squared e to the 1 minus e to the 1, then times 2 times 1, all over 1 to the exponent 4. So we get a numerator of e minus 2e and a denominator of 1. That's negative e over 1, or in other words, just negative e. So what we know is that the tangent line that we're trying to determine the equation of has a slope of negative e, which is roughly negative 2.7. Okay. Now so we know our slope is negative e. Now we also want to figure out what is our y coordinate. So we're missing an equal sign here, but at x equals 1, our y coordinate will be e to the 1 over 1 squared. That's e over 1, which is e. So now we know that the point in question is the point 1e, and the slope in question is negative e. So instead of saying y equals mx plus b, we can say y equals negative ex plus b. And subbing in an x value of 1 and a y value of e, we get e is equal to negative e times 1 plus b, so b is equal to 2e. So m is e and b is 2e, sorry, m is negative e and b is 2e, and so that means the equation of our line is y equals negative ex plus 2e. Now let's differentiate this function here. If f of x is 5 to the x, then f prime x is simply determined by restating the function exactly as it is, multiplying by the natural logarithm of the base of the exponent, so ln 5, and then multiplying by the derivative of the exponent itself. Well, the exponent itself is x, so the derivative of that is 1. So we get 5 to the x times ln 5 times 1, or in other words, we can say the derivative is simply 5 to the x ln 5. Now, what if we have something a little bit more complicated? Well, if we have 5 to the 3x minus 2, to determine that derivative, we'll simply follow the steps of rewriting the expression exactly as it is, then multiplying by the ln of the base of the exponent, and then multiplying by the derivative of the exponent. So the derivative of 3x minus 2 will just be 3. And that's what we have written here. And then at the end, instead of saying ln 5 times 3, we're just writing it as 3 ln 5. Okay. It's important to note that we do not say that in this context that ln of 5 times 3 is equal to ln 15. We're not multiplying that 3 and that 5. That is absolutely not what we're doing. Instead, the entire quantity ln of 5 is being multiplied by 3. Now, if we wanted to differentiate this function, again, this is a great example of an exponential function where we have x's in the exponent, but the base of the exponent is a scalar. So the process is to simply rewrite the exponent without even thinking, rewrite the function, without even thinking too much about it. Then multiply by the natural logarithm of the base of the exponent, which in this case is just the 7, and then multiply by the derivative of the exponent itself. So the derivative of 9x squared minus 5x plus 1 is 18x minus 5. And that'll be our derivative. And here it is shown a little bit more neatly. Okay. Now let's look at a word problem here. Imagine that on January 1st, 1850, the population of Gold Rush Town was 50,000. But since then, it can be expressed by the function shown. And we're going to assume t is the number of years since 1850. Okay, it's not written in the question, but it should be. Well, we want to know the population of Gold Rush Town on January 1st, 1900. What that means is that t equals 50 because it's been 50 years since that date right there. So letting t equal 50 and just plugging it in, we literally let our calculator do the work here. We get 50,000 times 0.98 to the exponent 50, and that's roughly 18,208. So the population of Gold Rush Town on that date we're asking about would be 18,208. Now, we want to know what rate the population was changing on that date. So what we're going to have to do now is determine the derivative. So the original function was 50,000 times 0.98 to the exponent t. That's what the population was with respect to t. So to determine that derivative, you'll notice all we do is we rewrite the function, then we multiply by the ln of the base, and then we multiply by the derivative of the exponent. Well, the exponent's just t, and so the derivative with respect to time will be 1 of that. So this is going to be our derivative. So plugging in a t value of 50, because we're asking about a time when t was equal to 50, plugging that in, we'll get negative 368. And so now we ask ourselves, what was p being measured in? And p was population, so p was being measured in people. And what were we differentiating with respect to? Time. But what were we measuring time in? Years. So the units on that derivative on this negative 368 is actually people per year. So we can say the population was decreasing at a rate of approximately 368 people per year on the date given. Now, here's another example of a radioactive substance decaying exponentially. So the percent of the material left after t years in this question is 100 times 1.015 to the exponent negative t. we want to determine the half-life of this substance. So we're going to let the percent remaining be 50. If we started with 100%, whenever we're left with 50%, we will have gone through one half-life. So we're going to let the amount remaining be 50%, and now we're going to solve for t. So 50 equals 100 times 1.015 to the exponent negative t. Dividing both sides by 100, we get 0.5 equals 1.015 to the negative t. Now, recalling our logarithms, that just means that negative t is the logarithm base 1.015 of 0.5 by the definition of a logarithm. So we get negative t is negative 46.6, or in other words, t is 46.6. T is measured in years, and so it took us 46.6 years to get to 1/2 of the original population. So what that means is the half-life is roughly 46.6 years. Now, we'd like to know how fast the substance is decaying at that time. So what we're going to do is determine the derivative. So if you recall, our original function was P of t equals 100 times 1.015 to the exponent negative t. So we're going to say P of t equals 100 times 1.015 to the exponent negative t. Now we're going to determine the derivative of that. And how do we do it? Well, we're going to simply, to determine that derivative, we're going to say that we have P prime of t equaling 100 times 1.015 to the exponent negative t times the ln of 1.015 times the derivative of the exponent, which will be negative 1. Okay? And so there should be a negative 1 at the end here. It looks like it's missing. Okay? And there we go. Yeah, so it looks like it's missing there, so there should be that negative 1. Now, when you multiply through 100 times 1.015 to the exponent negative 46.6 times the ln of 1.015 times negative 1, you get roughly negative 0.74. So what that means is at the time the half-life is reached, the substance is decaying at a rate of roughly 0.74% of the original amount of the substance per year. Now, how do you know to word it that way at the end is what sometimes confuses people. Well, just remember, in this case, P refers to percent of the substance, and T refers to number of years. So if I have a derivative equal to negative 0.74, that refers to 0.74% of the original amount of the substance, and then per year.